we're going to conclude our unit on heat and energy by looking at the laws of thermodynamics. And I'm going to describe them to you in the abbreviated version. And we're going to start off with the 0th law, which was identified fourth. Anyway, it really looks at the transitory properties that you might use in math, but if object A and B are at the same temperature, so say 30 degrees, and objects B and C are at the same temperature, say 30 degrees, because it was 30 up here, then objects A and C will be at the same temperature, which is 30 degrees. And that just makes logical sense, all of them are at the same temperature. Now the first law of thermodynamics, which was identified second in the four laws that we have up here, talks about how energy cannot be created or destroyed. It is within a system, it's only transferred, and we dealt with heat loss or removed is equal to heat gained, and that's when we used our little pieces of metal and we saw how temperature changed for both of them at the same time. And because of this, we need to account for the energy. What happens to some of the energy that we have out there is that it becomes unusable. And I've talked already about the radioactive energy that we have as waste now. And the second law of thermodynamics deals with objects that are not at equilibrium. So if they're not following this thing here, what happens to it? Well, then we know that heat travels from a hotter or a higher temperature to a lower temperature. So if we have something hot, the heat transfers to the object that is cold. And this continues until both of them meet equilibrium or the same temperature. Now, the second part of the second law of thermodynamics, which by the way was the first one to be identified, talks about the measure of entropy. Now, entropy is a measurement of randomness or disorder. And in nature, all things go from a very organized or ordered system to a disordered system or disorganization. And we can look at this in examples in terms of phase changes. In a solid, we talked about how the particles were nicely organized, they had low energy, so therefore they would keep their shape. As we add heat to the system, the particles start moving faster, and therefore they're able to spread out a little bit more, and they take the shape of their container, so they have a little bit of movement more than they did as a solid. Well, as we go to the gas phase, we know that the particles are moving so quickly that they bump into each other and they have all this movement, and at no given time can we truly predict where those objects are going to be at. And we have a really quick demonstration for you with using a deck of cards. If I have a deck of cards here that are organized in terms of lowest number to highest, and I have all the spades organized, then I have the hearts all organized from lowest to the highest value, then I have all the clubs organized again from the lowest to the highest value, and then I have the diamonds from the lowest to the highest value. Well, there's only so many ways that I can organize my cards. I can look at it in terms of all the aces, all the four aces together, all the four twos together, all the threes together. There's only so many ways that I can actually organize my deck of cards. But if I release the deck of cards out into the open and I just let them fall, every time that I pick them up and reorganize them, I can never predict if they're going to fall exactly the same every time, because there's so many different ways of randomness that we can never truly predict it. And that's what this measure of entropy is. The more disordered it is, the more random it is, and the higher the probability of this disorganization to occur. The third law of thermodynamics talks about absolute zero. And absolute zero, if you recall, is that state where matter would have no motion. In other words, the particles would stop moving. Here we have extremely slow motion, while they would even have zero motion. And if we have zero motion, we wouldn't have any entropy. But Einstein came up with his basic formula that if energy is equal to mass times velocity squared, speed of light over there, then it's not possible for us to have zero entropy, because if you have energy, you need to have matter, and if you have matter, therefore you will have entropy. So really, this law here, absolute zero, is a theoretical spot, but it helps us understand how the movement of heat goes in from one system to another. And that concludes our unit on energy and heat.